Hey guys, Mr. Backwork here. In this video, we're going to look at points of inflection.
So a point of inflection is a point on the graph of a function where there is a tangent line, so where the derivative does exist, and where the concavity changes. So as we're looking at this picture of x cubed, here in the middle at the x value of 0, the derivative exists there. And as we can see from the picture, on the left-hand side, the graph is concave down, but on the right-hand side, the graph is concave up. So the derivative exists here at the x value of 0, and our graph is changing its concavity, so there is a point of inflection at the x value of 0. So we're going to take a look at that same exact function. We've got the equation y equals x cubed, but we want to find the points of inflection by using some calculus ideas. So what we want to do is to find a point of inflection, we're looking for where the concavity changes. To help us figure this out, we're going to need to find the second derivative. Well, the first derivative of x cubed is going to be 3x squared from using the power rule. But then if we do another derivative, again using the power rule, this is going to be 6x. Now what we want to find are the critical numbers of this second derivative. So I'm going to take the 6x and set it equal to 0, divide the 6 over, and we get x equals 0 as a critical number. So if I think about making a sign chart, I've got 0 in the middle. I want to pick a test value from the left, so maybe I use -1. And then I want to pick a test value from the right, so maybe I use +1. So I'm going to take this -1 and plug it into my second derivative. So if I plug in -1 for the x, I get -6. The answer itself doesn't matter. The only thing we really care about is the sign. We got a negative answer, so that's a negative interval. On the right-hand side, if I plug in +1, then I get +6. That's a positive answer, so this is a positive interval. Now, points of inflection happen where the second derivative changes from positive to negative or vice versa, negative to positive. But it happens where the second derivative changes signs. So we can see at the x value of 0, we're changing signs. We're negative on the left-hand side, but positive on the right-hand side. Being negative on the left means that our graph is concave down on the left. Being positive on the right means that our graph is concave up on the right. And because we're changing our concavity at the x value of 0, then we can say that there's a point of inflection at the x value of 0. Now, if we want to figure out the actual point, then we would want to take this x value of 0 and plug it back into the original function. So plugging in 0 here and cubing it, we get 0. So the point 0, 0 is our inflection point. Now, taking a look at this example, we're going to find the points of inflection for the function y equals e raised to the -x squared. So the first thing we're going to have to do is find the second derivative. The first derivative, this is an e exponential, so when we do its derivative, it just stays the same. So we get e to the -x squared. But because there's extra stuff happening in that power, then we have to do the chain rule. So if we do the derivative of -x squared, we're going to get -2x. So that's the first derivative. Now, as we're finding the second derivative, there's now multiplication happening in here. So we're going to have to use the product rule. So the e to the -x squared is going to be our u value, and the -2x is going to be my v value. So for the product rule, we're supposed to leave the first piece the same, but then attach the derivative of the second piece so that -2x derives just into -2. And then we're going to add on, this time leave the second piece the same, but then attach the derivative of the first piece. So now we're doing the derivative of the e to the -x squared. Well, again, that's an e exponential, so it stays the same, but we have to do the chain rule because there's extra stuff happening in the power, so that derives into -2x. Now, we can clean this up just a little bit on the back end. If we take this -2x in front times this -2x on the end, then that's going to turn into 4x squared. And this still has e to the -x squared attached to it. And in the front, we have e to the -x squared attached to a negative 2. Now, since both of these have e to the negative x in them, we can actually factor that out as a GCF. Now I'm going to rearrange this. I'm going to put the 4x squared in the front, and I'm going to put the minus 2 on the end. So we're going to use our second derivative as e to the negative x squared times 4x squared minus 2. But we don't want to just find the second derivative. We want to figure out where the second derivative is equal to 0. So, because this is in its factored form, to find the zeros of this second derivative, we're going to take each individual factor and set them equal to 0. So first I'm going to take the e to the negative x squared and set it equal to 0. And then I'm going to take the 4x squared minus 2 and set that equal to 0. Now, if I were trying to solve this first piece, because we've got an e exponential, we would technically have to do the natural log of both sides to cancel out that e. But on the right-hand side, we can't actually do the natural log of 0. That's an undefined operation. So this one isn't going to give us any zeros. So let's focus on the other piece. I'm going to add the 2 over to the right-hand side. So we get 4x squared equals 2. I'm going to divide the 4 over, and I'm going to reduce my fraction, so I get a half. And then I want to square root both sides, so I get an x value of plus or minus the square root of 1/2. Now I'm going to draw out my sign chart. So I've got negative square root of 1/2, and I've got positive square root of 1/2. Now, as we're looking at picking some test values, it's maybe not real easy to do the square root of a half, so I would punch that into my calculator, and it ends up being about 0.7. So this is negative 0.7, and this is positive 0.7. So here I want to pick something to the left, so maybe I pick negative 1. So if I store key that negative 1 and then plug it into this second derivative, we get a decimal of about 0.74. Doesn't really matter what the number is, it just matters that that answer was positive. Now in the middle here, I want to pick something between negative 0.7 and positive 0.7. We change signs there, so it's going to be safe for us to test 0. So then I'm going to store key 0 and plug that into my second derivative. When we do that, we should get negative 2 as our answer. And again, the number itself doesn't matter. We just care that it's a negative answer. And then I want to plug in something to the right of 0.7, so maybe I just plug in 1. So I'm going to store key 1 in my calculator and plug it into that second derivative again. And I get about 0.74 again, so that's going to be a positive interval. So we can see from our sign chart, our graph is concave up on the far left-hand side, concave down in the middle, and then concave up again on the right-hand side. So we have points of inflection happening at negative square root of a half and positive square root of a half. Now, to figure out what those points actually are, we're going to take each one of these x values and we'll have to plug it back into the original function. So just a reminder, our original function was y equals e to the negative x squared. So if I plug in this negative square root of 1/2, then this would say e to the negative square root of 1/2, all being squared. Well, when you square something that's negative, it turns positive. And then when you square a square root, that cancels out. So this is really going to say e to the negative 1/2 power, which we don't typically like to deal with negative powers. So what I can do is drop that e down to the bottom of a fraction to turn that power positive. But then a half power is really just the same as the square root of e. So for that first inflection point, we plugged in negative square root of 1/2, and we got an answer of 1 over the square root of e. But now we still want to plug in that positive square root of a half. So we get e to the negative square root of positive 1/2 squared. Well, when you square something that has a square root on it, those just cancel each other out. So this becomes e to the negative 1/2, which is what we just got done dealing with. So that's just going to turn into 1 over the square root of e again. So then the actual inflection point is at the square root of 1/2 and then 1 over the square root of e. So these are our two inflection points. Now, this example is a little bit different. Here, what we're going to be doing is reading the graph of a derivative and using it to help us find out information about the original function f. So this graph that we're given down in the bottom right-hand corner is the derivative of some function f over the interval from -4 to 4. And like I said, we're going to answer a whole bunch of questions based on this picture. And the first thing that we want to figure out is on what intervals is the original function increasing. But we have to remember that this isn't a graph of the original function. This is the graph of the derivative. And a function increases when the derivative is positive. So we're looking for places where this derivative picture is positive. So on our graph, being positive means that it's above the x-axis. So starting at that -4 value until we hit that value of -2. Now, when I wrote out this interval, this -4 gets a square bracket because it's included. That point is above the x-axis, but -2 is not included because that point isn't actually above the x-axis. It's right on the x-axis, so we can't include it because it's not greater than 0 there. But then we've also got an interval that goes from -2 to 1, and both of those are going to get open parentheses around them for the same reason. It's equal to 0 there, but we need our derivative to be bigger than 0, so we don't include those endpoints. Now, these are consecutive intervals, so we can technically put them together and say that we're increasing on the interval from -4 to 1, but something special is happening at this x value of -2. Since our derivative is equal to 0 at that x value of -2, there's technically a horizontal tangent line happening at the x value of -2, but our graph doesn't change from increasing to decreasing there, so we call that a shelf point. So we've got a shelf point happening at the x value of -2. Now, the next thing we want to take a look at is any intervals where the graph of our original function f is concave up. Again, we have to remember that this graph is of the derivative of our function. So if we want to figure out where the graph of our original function is concave up, then we need to look for where the derivative is increasing. So where the derivative is going up. So there's two places on our graph where our picture is going up. One place I see is from -2 to 0. We can see that the graph of our derivative is going up there, but then it switches to going down. But then again, at the x value of 3, until we hit the x value of 4, we can see that our derivative is going up there as well. So our original function f is going to be concave up on these two intervals. The next thing we want to find are any x-coordinates where our function f would have a local extreme value. Now, based on the first derivative test, extrema happen where your derivative changes sign. So where your derivative goes from being positive to negative or negative to positive. And there's one place on the graph where it changes signs. On the left-hand side of our graph, that's all positive. On the right-hand side of our graph, that's all negative. But we change signs at the x value of 1. So there has to be some sort of local extrema happening at that x value of 1. And because our derivative goes from being positive to negative, that has to be a local maximum. Now, we also want to take a look at the endpoints of our derivative as well. So looking at the x value of -4, because our derivative is positive to the right of that left endpoint, then we have to have a local minimum there. And also, as we're looking at the right endpoint of 4, because the derivative is negative to the left of that right endpoint, then we've also got a local minimum happening there as well. Next thing on the agenda are finding the x-coordinates of the inflection points for our function f, and those are going to happen at the turning points of the graph of the derivative. So we can see that our graph turns or changes directions at the x value of -2, at the x value of 0, and at the x value of 3. So those are going to be points of inflection for the original function f. Now the last thing we want to do is use all of that information to try to help us sketch out a possible picture for our graph. So starting on the far left-hand side, our derivative was positive, so that means that the graph of the original function has to be increasing. So if I start down here on the bottom corner and I go up, I increase. Now one thing we said was at the x value of -2, we were going to change our concavity. So I guess the way I'm drawing my graph right now, it's kind of concave down, but at the x value of 2, it's going to have to change its concavity, and I'm going to make it be concave up now, but it's going to keep increasing. Maybe not quite that steep, but it's going to keep increasing. Now we said that there was going to be a local maximum point at the x value of 1. So we're going to keep increasing until we hit that x value of 1, but then because we've got a local maximum, our graph is going to have to start going down. And this should make sense to us because our derivative here after that x value of 1 was negative, so that means that our graph has to be going down, and we're going to keep going down. Now we said that there was going to be a point of inflection at the x value of 3, so right now my graph is kind of concave down because it's got that curve coming down. So at 3 I need to switch and maybe start flattening out the other way so that I get that concave up look to my graph. So this is just a potential sketch of the graph based on that information that we were just looking at. Now, as we're talking about points of inflection, we do want to be a little careful. It's sort of tempting to oversimplify a point of inflection as saying that it's a point where the second derivative is equal to 0, but there are two reasons why that could be incorrect. One of those is that the second derivative could be 0 at a non-inflection point. Just because your second derivative is equal to 0, that doesn't necessarily mean that it's changing signs. So that's why we make our sign chart to help us see if that derivative is in fact changing signs. And then the other thing is that the second derivative doesn't actually have to be 0 at an inflection point. The concavity of a graph could also change at a vertical tangent line, so the first derivative and the second derivative wouldn't exist there, but there still could be a point of inflection. Now the last example we're going to do here is a little motion along a line problem. So we've got a particle moving along the x-axis, and we've got this position function x of t equals 2t cubed minus 14t squared plus 22t minus 5 for t values that are greater than or equal to 0. We want to find the velocity and acceleration, and then we also want to describe the motion of this particle. So the velocity function, we can call that v of t. The velocity function is the derivative of your position function. So we're going to use the power rule in here to help us find this derivative. So drop the 3 down as a multiplier, and that becomes 6t squared. Drop the 2 down as a multiplier, and that becomes negative 28t. And then the derivative of 22t is just 22. Now we can actually factor this out a little bit. All of these numbers are even, so I can pull out a GCF of 2. So then this is going to be 3t squared minus 14t plus 11. But this quadratic also factors out a little bit. So this is going to be 2 times. Now because of this 3t squared, we're going to need a 3t and a regular t when we do our factoring. There's not a whole lot of things that are going to multiply to 11 but add up to negative 14 with this 3 in here. So this 3t is going to have to get a minus 11, and this regular t is going to have to get a minus 1. So this is our velocity function in its factored out form. Now the reason why we went ahead and factored it right away is as we get to the part where we're going to describe the motion of our particle, being able to easily find the zeros of this derivative is going to be important to us. Now the next thing we want to find is the acceleration, and the acceleration is the derivative of the velocity function. I think it's going to be easiest to look at the non-factored form first. So we do the power rule there, drop the 2 down as a multiplier, and we get 12t. And then if we do the derivative of the negative 28t, that's just negative 28. Now this one we could do a little GCF factoring, but I don't think it's really necessary. This itself is going to be easy enough to find the zeros of, whereas the quadratic in the previous one may have been a little difficult, so it's going to be easiest to have that one in its factored form. So we've got our velocity function and we've got our acceleration function. Now as far as describing the motion, we're going to make some sign charts in here. When our original x of t is increasing, that's going to mean that our particle is moving to the right. And when our x of t is decreasing, that's going to mean that our particle is moving to the left. Well, to figure out when your function is increasing or decreasing, we want to make a sign chart using the derivative. So I want to find the zeros of the derivative, which is why we got it in its factored form. So we're going to have a 0 at t equals 11 thirds and at t equals 1. So I'm going to make a sign chart in here. So we've got the 1 and we've got the 11 thirds. We want to pick a test value to plug in. So something to the left of 1, I'm going to test out 0, and I'm going to plug that into this derivative. So if I plug in zeros for those t's, I'm going to get a positive answer there. So that's a positive interval. Then I want to plug in something between 1 and 11 thirds. So maybe I plug in 2. Well, if we were to store key that and plug that into our velocity function, we would get a negative answer. So that's a decreasing interval. And then if I want to plug in something to the right of 11 thirds, I would have to choose maybe something like 4. If I store key that and plug that into my derivative, I get a positive interval there. So based on our first derivative sign chart, we can see that our original function is increasing on the left-hand side. So that means that our particle is moving to the right. In the middle, we've got a negative derivative. So our original function is decreasing, meaning that our particle is moving to the left. And then on the right-hand side, we've got a positive derivative again. So our original function is increasing, meaning that our particle is moving to the right. Now, as far as using that second derivative, that acceleration, when the acceleration is positive, that means that your particle is speeding up. But when the second derivative is negative, that means that your particle is slowing down. So the first thing we would have to do is find our 0 in here. So I'm going to take the 12t minus 28 and set that equal to 0. Add the 28 over, divide by the 12, and do a little reducing. We get a t value of 7 thirds. So we've got our sign chart, and we're using 7 thirds in the middle here. Well, we want to plug in something that's smaller than 7 thirds, so we could plug in 1. If we plug that into our second derivative here, we get a negative answer. And then if I plug in something to the right of 7 thirds, maybe I plug in 3. Plugging that in, we get a positive answer for that second derivative. So on the left-hand side, because we have a negative second derivative, that means that our particle is slowing down, or we can say that it's decelerating. And because on the right-hand side, we have a positive second derivative, that means that our particle is going to be accelerating or speeding up. That's going to be it for this video. Thanks for watching.